All right, so welcome to our last Wednesday class of the quarter, believe it or not. We're definitely in the home stretch. So the plan today is to hit the last topic under applications of derivatives, which are these things called antiderivatives, which are exactly what they sound like. They're the opposite of derivatives. So that's our goal for today, is to talk about those. But before we get there, I'm going to open it up to you guys. Any questions about any homework or anything else we've been talking about in class? All right, Alia. All right, so Alia says she'd like to see number 5. And you say on 4.7 and 4.8, you mean number 5 on each of those sections? Yep, okay. I'll go ahead and put that on the list. Anything else? All right, well then let's go ahead and hop over and take a look at those and see what we can do. Four, 7, and 4, 8. Okay, so 4, 7 is going to be a applied max min. So let's get that pulled up. All right, so something funky happened with my computer, so well, looks like I might be back up. I'm going to go ahead and just do it here. So I'm not going to be able to show you on the computer what the question is, but I'll talk through it. All right, so give me just 1 second. I'll be right back. All right, so for question number 5 from 4.7, it says a fence 12 feet tall runs parallel to a tall building at a distance of 6 feet from the building. We want to find the length of the shortest ladder that will reach from the ground over the fence to the wall of the building. Okay, so let me draw a picture and then we'll kind of walk through how we're going to solve this. All right, so here's our picture. We got our ground. We got the building. All right, so like any good building, we got to have some doors and windows and whatnot. Right? And then we've got a fence that's over here. We're told that that fence is 12 feet tall. And that it's 6 feet away from the building itself. So we're going to lean a ladder against that fence so that it touches the wall. And we want to figure out what is the shortest possible length we can have. All right. So it says that we want to start by finding the length of the ladder in terms of the angle theta that's made with the ground. All right, so let's see if we can create a formula for the length of this thing. And what it suggests that we do, it says to split the ladder into 2 parts. So those 2 parts, it should be pretty clear what those 2 chunks are going to be. If you look at this red line right here, there's the piece that's from the ground to the fence, and then the part that's from the fence up to the wall. All right, so let's call those maybe X and Y. So let's get a formula for X and then for Y in terms of theta. All right, so let's look at X first. We've got a little right triangle here. It looks like this. We've got theta, X, and 12. So if we want to get a formula for X and theta here, we're going to want to use a trig function. So which trig function is going to relate those 2 sides, the sides 12 and X? Yeah, it's going to be sine, because sine is opposite over hypotenuse. So we know the sine of theta is equal to 12 over X. So X is equal to 12 over sine theta. And I'm going to rewrite that as cosecant, just because I would rather not have a fraction. So this X is going to equal 12 cosecants of theta. All right, so cool for X. So now let's find Y. Now, if we want Y in terms of theta, what I'm going to do is I'm just going to draw a little horizontal line there. There's my theta. So let's look at that smaller triangle that involves Y. So if we draw that one, it looks very similar, right, with the theta and the Y there. But now we don't know its vertical side. I have no idea. But I do know its horizontal side is 6. So we're going to do exactly the same thing. We're just going to use a different trig function. Now, instead of sine, we're going to use cosine. So we've got the cosine of theta is equal to 6 over Y, or Y is equal to 6 over cosine, which, again, I'm going to rewrite that as secant. So the length of this ladder, then, it's equal to 12 cosecant of theta plus 6 secant of theta. So if you tell me what the angle is, I can punch that in there, and that will tell you how long our ladder is. So that was the first part. It says, let's get a length in terms of theta. Okay, so now what we're going to do is we're going to differentiate this. So basically, we're going to figure out what theta is going to give us our minimum value, which then, when we plug it in, will give us our length. All right, so any questions at this point? And I just need to let you guys know, since I don't have my computer and I'm just using this screen, I'm not going to be able to see chat as well. I will definitely try to pay attention to it, but just realize I might not catch if you type something in chat for a bit. Okay, so let's go ahead and differentiate this then. So if we differentiate with respect to theta, we get L prime is equal to, well, the derivative of cosecant. Don't know if you remember this one. It's negative cosecant cotangent, so we're going to get minus 12 cosecant cotangent. And the derivative of secant is secant tangent. So the derivative of 6 secant is 6 secant tangent. So there's our derivative in terms of theta. So that's the second thing that they actually asked us to figure out. Okay, so now we need to figure out where this equals 0 or where it's undefined. All right, so this is actually where I'm going to go back and turn these into sines and cosines. So I'm not going to worry about where it's undefined, because where it's undefined is either going to be at angles of 0 or pi over 2. And both of those don't make sense. An angle of 0 means the ladder is lying on the ground. That's never going to, we're never going to clear the fence that way. An angle of pi over 2 means it's sticking straight up. Well, then it's not resting against the building. So I'm going to not worry about where this is undefined. Instead, I'm just going to look at where this is equal to 0. So let me rewrite this in terms of sines and cosines. So I've got minus 12 cosine of theta over sine squared theta. Because cosecant's 1 over sine, cotangent is cosine over sine. The other one, I get plus 6 sine of theta over cosine squared theta. And I want to know where that equals 0. All right, so I'm going to go ahead and multiply by sine squared cosine squared just to get rid of the fractions here. So I get minus 12 cosine cubed plus 6 sine cubed equals 0. If I rewrite this, move the 12 cosine cubed to the other side. And then I'm going to divide both sides by 6, just to simplify this a bit. So I get sine cubed equals 2 cosine cubed. And now the next step is maybe one that you wouldn't have thought about, but I'm actually going to divide both sides by cosine cubed. Because what that's going to do is turn this left side into tangent cubed. So I've got tangent cubed equals 2. Well, solving that for tangent gives me tangent of theta equals cube root of 2. And so this is the angle that I need. I need to find out what angle essentially gives me a tangent of the cube root of 2. All right, well, that's easy enough. We can use our calculator. So theta is going to be the inverse tangent of the cube root of 2. So your calculator is going to give you that angle. And then once you've got that angle, you can plug that in back into here. And that will give you, oh, no, sorry, not into there. That's just going to give you 0. You want to plug that angle into our original length formula. And that will tell you how long that ladder is. And that'll be the shortest possible ladder that's going to clear that fence and touch the building. All right, so this one definitely required some trig tricks, but hopefully that makes sense. All right, so any other questions on this number 5?
No, I think that's good, even though that was pretty terrible.
So I mean, you say that's good, meaning you understand what's going on, but you said even though it's terrible. So what's terrible about it?
I think for me, just all of the trig. I don't know. There's just a lot of steps that would have taken me a long time to figure out, but like watching you do them, I can follow it. So
Yeah, and I'm not surprised to hear that. Trig is one of those things that if you see it, if you see the trig steps, it can end up being really, really easy. If you don't see the steps, it's virtually impossible, right? So I'm not surprised to hear that a lot of times with things with trig, that's an issue. The other thing I am going to mention though is that if you've got like a TI-89 or access to something else on your computer, there are things that will solve these equations for you. So you could just type in solve minus 12 cosecant cotangent plus 6 secant tangent equals 0, and it will get you this answer. And that's always fine as well. Like on an exam or something, I'm really looking for, do you have this formula for that you're trying to optimize? Did you differentiate it properly? I'm not as concerned about the steps to get you to this, right? Like all this stuff over here, that's more trig and algebra. I'm looking at calculus understanding, you know what I mean? So don't hesitate if you're, especially if you're like in a bind, you're like, man, I have no idea how to solve this on my own. Go ahead and use your technology to do that. Okay, let me pull up the other question here, which is same number, but from section 4.8. So this is L'Hopital's rule. All right. Okay, so for this one, we're looking at a limit as x goes to 0 of 10 to the x minus 11 to the x divided by x. All right, so this is also number 5, but from 4.8. All right, so like any other limit, good place to start is by trying to plug in 0, see what we get. On the bottom, we get 0, which already the alarm bells should start going off. If we plug it into the top, 10 to the 0 and 11 to the 0 are both 1. So we get 1 minus 1, which is 0 over 0. So that's an indeterminate form, which means we want to try L'Hopital's rule. All right, so the idea with L'Hopital's rule is that we're going to get the same limit if we differentiate the top and bottom functions independently and keep that fraction. So let's see what that does. The bottom, the derivative of x is 1. That's nice and easy. 10 to the x, that's exponential. Its derivative is going to be the natural log of 10 times 10 to the x. The 11 to the x is going to give us natural log of 11 times 11 to the x. So exponential functions are really easy. You just differentiate, you get the same thing, but then you have to multiply by the natural log of the base. All right, so now let's plug in 0. Well, we don't have to worry about division by 0 anymore because we're just dividing by 1. So plugging in 0 is going to give us natural log of 10 times 1. So natural log of 10 minus the natural log of 11 times 1, which is just the natural log of 11. All right, so there's your limit value, the natural log of 10 minus the natural log of 11. There are a lot of things we could do to this. If you wanted, since it's a subtraction of logs, we could write it as the log of just 10/11ths. So natural log of 10/11ths. You can punch this into your calculator and get a decimal. That's fine too. But there's the limit for this function. And Ollie, when I actually saw this one, I know that you sent me a message about it, and I replied, I don't know if you saw. But I think the only issue with yours was that the calculator or computer wanted more decimals, even though it didn't tell you.
Oh, gotcha. Okay.
You actually did it properly. The number that you found was correct.
Okay.
It's just probably a tolerance thing with the computer.
Okay, great. Thank you.
You're welcome. Anyway, but there you go. L'Hopital's rule to the rescue makes solving these things or finding these limits really easy when you're in an indeterminate form. All right, so any other questions on homework stuff before we hit
I have one more.
Yeah, go for it, Dan.
Could you do L'Hopital's for 4.8 question 7?
Sure.
It's just one of the trig function.
We can definitely do that.
I figured out how to like extract the answer from the question, but I don't really understand why it works.
Okay. And I totally know what you mean by that, because you do start getting patterns to this, and you can start seeing how like when you've got multiples of angles and all that, where those fall in. But yeah, we'll go ahead and walk through this. So we're looking at a limit as x goes to pi over 2. And we've got 6 cosine of minus 5x times secant of 9x. Okay, so if we were to take pi over 2 and plug it in, cosine of minus 5 pi over 2 is going to be 0. And the secant of 9 pi over 2 is undefined. It actually goes towards infinity. So this form, if we plug it in, is 0 times infinity. So 0 times infinity is an indeterminate form, which means we're going to want to use L'Hopital's rule, but we got to do something to it first, because you can't do L'Hopital's rule exactly in this form. What do you have to do to make it L'Hopitalable?
Take the derivative?
No, gotta do something before I take derivatives. What do you have to do when you have 0 times infinity?
Plug in the limit?
Nope. If I plug in the limit, that tells me 0 times infinity. Because what are the forms that L'Hopital's rule works on?
Oh, 0 over 0, infinity over infinity.
Yeah, we need to get it either 0 or 0 or infinity over infinity. So I have to basically divide by one of these. So like Ayers would put there, convert to a fraction. That's exactly what I want to do. And there's a really natural way to do it with trig functions. All you got to do is change it into its buddy function. So like this one, cosine, I could turn that into a secant, or the secant I could turn into a cosine. Well, I'm going to turn the secant into a cosine. I'm going to rewrite this as 6, so limit as x goes to pi over 2 of 6 cosine of minus 5x divided by cosine of 9x, because secant is 1 over cosine. And now, if I plug in pi over 2, again, I'm going to get 0 on the top. We already knew that. But cosine of 9 pi over 2 is actually also 0. So this is now in the form for L'Hopital's rule. So my suggestion, if you ever have secants or cosecants, turn them into sines or cosines in the other part of the fraction, and it usually will get you into the form for L'Hopital's rule. All right, so now let's do L'Hopital's rule. We need to differentiate the top and the bottom. So on top, the cosine becomes negative sine of minus 5x. And then we need to multiply by the derivative of what's inside. We have to multiply by negative 5. And that came from the chain rule. On the bottom, we're going to get negative sine of 9x. And again, we need to multiply by 9. So before I go and evaluate this limit, I'm going to simplify it a little bit. This is the limit as x goes to pi over 2 of minus 10/3 times sine of minus 5x over sine of 9x. So I just dealt with the numbers a little bit and pulled them out front. All right, so now let's plug it in. So we're going to get minus 10/3. So then we need the sine of minus 5 pi over 2. Well, that's going to be the same as the negative sine of 5 pi over 2. The sine of 5 pi over 2 is the same as the sine of pi over 2, which is 1. So that guy is negative 1. Or just punch it into your calculator. Okay, sine of 9 pi over 2. That's the same as sine of pi over 2. And the sine of pi over 2 is 1. So these are ones we can just evaluate. And it looks like we end up with 10/3. So again, L'Hopital's rule gets us to a form where we can just plug in. And this happens a lot with cosines and sines. If you've got values that make cosine 0, they're going to be nice for sine, and vice versa. Values that make sine 0 make cosine non-zero. So L'Hopital's rule is really good when you've got sines and cosines. All right, so that was you, Tim, right, that asked that? Is that good?
Yeah, that makes a lot of sense.
Okay. All right. So anything else? Are we ready to hit antiderivatives? All right. Well, then let's hit our last topic for this entire quarter. Oh my God, we're already there. All right, so chapter 4 has all been about applications of the derivative, things that we do with it. And this last thing I'm going to show you is probably not going to feel like anything new, because it's not really. It's just doing the same thing we've been doing, just backwards. All right. And so we're going to talk about what we call anti-derivatives. Okay, so this is what it means to have an antiderivative. We're going to say big F of x is an antiderivative of little f of x if big F prime equals little f. Okay, so this is the definition. Now I know when I write it like this, you're probably like, what? So first of all, a couple of things. Notice that I used a capital letter for my antiderivative and the lowercase for the function itself. And that's standard. That's not a Bruce thing. You will see that in every calculus book, and every calculus teacher will show you that. Okay, so that's the same regardless. But basically, here's how this plays out. The antiderivative, it's the function whose derivative is what we're given. Okay, so this is like Jeopardy. We're given the answer, and we're trying to find out the question. Given a derivative, can you tell me the original function? Okay, so an antiderivative is just going backwards. When we started with a function and we got its derivative, anti-differentiation is taking that derivative and going back to the original function. All right, so let me give you some examples. Like, let's say we have little f of x is equal to 1 over x. Okay, so we got 1 over x. The antiderivative is going to be a function whose derivative is 1 over x. So can you think of a function whose derivative is 1 over x? All right, thanks, Alia. How about natural log? Right, the natural log, its derivative is 1 over x. So an antiderivative is natural log of x. All right, here's another one. What if we have, say, g of x is equal to 4x cubed? Can you give me its antiderivative? So can you give me a function whose derivative is 4x cubed?
X to the fourth.
How about x to the fourth? Beauty, right? Because the derivative of x to the fourth is 4x cubed. So you're starting to see how this works? We're just going backwards. Now it's well, I just gave you the derivative. Tell me what the original function was. All right, so here's one more. Let's try h of x equals cosine of x. So what function would give me a derivative of cosine?
Negative sign.
All right, so I hear negative sign. Jessica just put in the chat box regular sign. It's definitely one of those. Well, in this case, yeah, Jessica had it. It's just sine, because the derivative of sine is cosine. All right, now this is where they're going to start getting a little tricky when you start doing antiderivatives of sine and cosine, because the antiderivatives look a lot like the derivatives, but they're not quite the same. All right, so this is the idea with antidifferentiation, is we're just going backwards. All right, so we don't actually have to learn anything new. We just have to train ourselves to go in reverse, right? So now it's oh, this is the derivative. Let's find the original function. Now, there is notation that we use for this because mathematicians, of course, we're lazy. And we don't want to write out, find the antiderivative of whatever every time. So let me show you the symbols that we use, that says find an antiderivative. All right, so if I want you to antidifferentiate, so to find capital F, this is the symbol that we're going to use. This is how we're going to write it. All right, so this kind of like curvy S looking thing, this is what we call an integral. So it's an integral symbol. When you see that, that tells you antidifferentiate. The function that we're antidifferentiating, of course, is the thing that's in here. That also has a fancy name. I'm going to tell it to you just in case you ever come across it. This is called the integrand. Of course. All right, so that's the integrand. I'm never going to call it that, but if you ever run across that when you're reading something and it says, oh, the integrand, blah, 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 just integrand just means what we're integrating, what we're antidifferentiating, what that function is that's the answer. And we're not trying to go backwards to. All right, so that's the integrand. And then, of course, you see our little differential here, dx. But this is very important because remember that this piece, this tells you the variable. So it's just like when we would write, say, dy dx or dy dt. We're always saying we're differentiating with respect to a variable. Well, the same thing happens when we antidifferentiate. We antidifferentiate with respect to a variable. And this is what tells you it, okay? So you definitely need all three pieces when you write an integral. You need the integral symbol, you need the thing that we're antidifferentiating, and you need to tell us what variable we have. Okay, so all of that needs to be there. But that's how a mathematician tells you to antidifferentiate. All right. So if I want you to find an antiderivative, I'm going to write it like this. So here we go. How about this one? Okay, so we've got an integral. So it's saying antidifferentiate. The function we're antidifferentiating is 1 over 1 plus x squared. And the variable is x. Okay, primarily we're going to use x, but it could be t, it could be, whatever. Okay, so can you give me an answer here? Can you give me a function whose derivative is 1 over 1 plus x squared? I think maybe I should change that question, because the can you, yes, it is possible. But do you remember the function whose derivative is 1 over 1 plus x squared?
Tangent inverse.
There you go. Beautiful. So this is going to be inverse tangent of x, because the derivative of inverse tangent is 1 over 1 plus x squared. Okay, so look for that symbol. That's telling us we're anti-differentiating. Now, there is another name for this, because of course there is. And this is what we call an indefinite integral. So that's another term you're going to hear. Someone will say, find the indefinite integral or evaluate this indefinite integral or whatever. That means anti-differentiate, okay? But this is an indefinite integral. And yes, there are definite integrals, and you'll learn about that next quarter. Okay, that's actually where we get, that's the first thing that we do starting in January. All right, so indefinite integrals. Now, I don't know if you've caught this, but as I've been talking about antiderivatives, I've been very careful with my choice of article. You know, articles, the, a, and, right, those kind of things. And every time I've said, let's find, when I talk about antiderivatives, I've always said, let's find an antiderivative. I've never said find the antiderivative. I've said find an antiderivative. So what does that mean? Well, it turns out that there's more than one antiderivative. Given a function, if you want to anti-differentiate, there's more than one choice. Wait, what? They come back to this one, the 1 over 1 plus x squared. So when I said, hey, can anybody give me an antiderivative for that? And I think it was Susanna who said it was inverse tangent. That is an antiderivative, no doubt about it. You differentiate inverse tangent of x, you're going to get 1 over 1 plus x squared. But it's not the only antiderivative. Let me give you another one. What if instead I gave you inverse tangent of x plus 4? Is its derivative 1 over 1 plus x squared?
Yes.
Yeah, that's pretty easy to see, because what happens when you differentiate that plus 4? Well, that plus 4 goes away. We've already seen that constants that get added or subtracted disappear when you differentiate. And so in reality, inverse tangent works, but also inverse tangent plus or minus your favorite constant. So what we're going to do is we're going to put plus c, because that plus c is going to allow for all of the possibilities. So you give me inverse tangent plus your favorite constant, and that constant can be negative, so you can also think of it as minus, whatever. But as long as we're adding or subtracting a constant, its derivative is still going to be the same. All right, so I just want you to get in the habit, when you have an indefinite integral, when you've got one of these guys, always put plus c. So let's do a couple more here. How about, let's get the integral of secant squared x dx. So can you think of a function whose derivative is secant squared?
Tangent.
Beautiful. So we're going to write this as tangent of x plus c. One more for good measure. How about what's the integral of e to the x dx? So what function gives us e to the x as a derivative?
Oh, I know this one. It's e to the x.
Yeah. Remember how e to the x was awesome? It was its own derivative. Well, it's also its own integral then. It's its own antiderivative. So the integral of e to the x dx is equal to e to the x plus c, because we could add any kind of constant. All right, so how are we feeling at this point? Not too bad, hopefully.
Do we have a better way of finding antiderivatives than just thinking about it?
Nope.
Okay.
I hate to break it to you, but no. That, like, this is a case of just remembering your rules. So, like, think about it. We could make a list of all our differentiation rules, right? Like the derivative of sine is cosine, the derivative of tangent is secant tangent, e to the x, natural log of x, 1 over x, and so on, right? Now we're just going backwards. So this is actually something I recommend you do. Make a list. Now, the list I'm going to write here is definitely not exhaustive because I don't want to do all of them. But like, make a list of all the different things you know. So like natural log of x, it's 1 over x, sine of x, it's cosine of x, inverse tangent, 1 over 1 plus x squared, and so on and so forth. And I mean, and we've got a ton, right? We've done an absolute ton of functions, because now when we're anti-differentiating, we're just going this way. So you want to look at the right-hand column and work your way back. So that's why, like with the integral of 1 over 1 plus x squared, you go, ooh, 1 over 1 plus x squared, that gives me inverse tangent. Boom. Right? Somewhere down here is, on our list, is tangent of x. Its derivative is secant squared. So like if you look at that second one there, integral of secant squared, ooh, secant squared, that's on my list. Its antiderivative is tangent. So the answer to Alia's question, and I hate to be this way, but no, there is no way of doing it other than, I just remember I know what the derivatives are, and now I just need to go backwards. But like I said, we're not learning anything new. This list is this list. We already know this list. We just have to train ourselves. We have to retrain ourselves when we're anti-differentiating to go the opposite direction. So unfortunately, no, there's no better way. All right. And I know in the book somewhere they give you like a huge long list like this. So you can definitely reference that to help you with this. All right, but there are a couple of rules I want to remind you about that were rules of differentiation that are also going to be rules of integration. So what did we do when we added and subtracted functions before? Like when we differentiated a sum or difference of functions, how did we differentiate them? And in case you're not quite sure what I mean by that, we had a rule that started like this: the derivative of f of x plus or minus g of x. How did we differentiate those? And this is also one of those rules that you don't even think about anymore. You just take for granted.
F prime x plus g prime of x.
Okay, good. So
What's
you
it?
just, you differentiate them separately and add or subtract, right? Well, since anti-differentiation is differentiation going backwards, we're going to have exactly the same deal. If we integrate a sum or difference, it's the same as integrating them separately. So you could have a string of like 5 functions that are being all added together. Just do them each one at a time. Okay, so we had that sum and difference. We also had a rule for constant multiples. What happened when we had a constant multiple and we differentiated? So like if you had 5 sine of x, or -2 square root of x, or whatever.
Does it become a constant?
That constant stayed, right? It stayed there. So this was the same as the constant times the derivative of f of x. All right, so that means if we're going to anti-differentiate, we're going to integrate with a constant multiple. It's the same deal. So just like when you differentiated, constant multiples stayed. When you integrate, constant multiples stay. So it's exactly the same rule. It's just now going backwards. Some other rules about the power rule. So now this one's going to be require us to think a little bit differently. But what was the rule for differentiating x to the n? This is another one you probably don't think about much anymore. But what do you do when you have a
You
power?
move the exponent to the front and then you drop it by 1.
Okay, good. So we multiply by that exponent, and then we decrease the exponent by 1. Again, it's one of those that you don't even probably think about anymore. You just automatically do. Okay, so what then happens if we integrate x to the n? Now, basically, this is just where we have to go, well, we're going in reverse. So think about what the steps were. We multiplied by the exponent and then decreased the exponent by 1. So if we're going to go in reverse, instead of decreasing the exponent by 1, we're going to increase the exponent by 1. Right? It's the opposite. All right. And then instead of multiplying by that exponent, what are we going to do? What's the opposite of multiply? Yeah, thanks, Eris, is divide. Now, I want you to notice that this is divide by n plus 1. And that's because when we did that multiplication at the very beginning, it was of the bigger exponent, right? It was that exponent before we changed it. So we have to divide by the bigger exponent, which is n plus 1. And to be good about this, I'm going to go ahead and put my plus C. But this is the power rule backwards. Instead of subtracting 1 from the exponent, we're going to add 1 to the exponent. And then we're going to divide by that exponent instead of multiplying. So hopefully you're kind of seeing the logic here. It's just we're doing everything backwards. We just have to do the opposite of what we did along the way. So let me show you a couple of examples with powers. It's pretty easy to do. So how about let's find the antiderivative of x squared. We're going to integrate x squared. So what we're going to get, we have to increase the exponent by 1. So it's going to be x to the third. And then we need to divide by that new increased exponent. So the antiderivative of x squared is x cubed over 3. All right, here's another one. How about the integral of the cube root of x? So first of all, remind yourself that that's x to the 1/3. So what we're going to have to do is add 1 to that. We've got x to the 4/3. And then we're going to divide by 4/3. So I am going to rewrite that, make it a little bit nicer. It's going to be 3/4 x to the 4/3 plus c. So there's the antiderivative of the cube root of x. I know, now all of a sudden there's fractions, and you're like, oh, fraction. That same pattern. We're doing exactly the same thing that we've done every other time. Don't let the fact you're dividing by a fraction freak you out. All right, so how about we'll do one more. 1 over x. So again, as an exponent, this is x to the -1. All right, so add 1 to the exponent. What do we get? It's not a trick question. There you go. Thanks. It's 0. So we get x to the 0. And then what do we have to divide by? Zero. And this should make every single one of you unhappy.
That's illegal.
That is very illegal. Uh-oh. Okay, so there is a bit of an issue here. Like this rule that I gave you doesn't always work. There is one exception. We can't have n equal -1 because obviously that leads to division by 0. But other than that, the power rule totally works. Okay, so, scheisse, I can't use that. Oh, but this is trickeration. What function gives us derivative of 1 over x? You already know this. In fact, natural log. I asked you to do this earlier. This is the natural log of x plus c. Okay, so for powers, you can always use the power rule. Do this, add 1 to the exponent and divide by that number. With the exception of an exponent of -1, but if your exponent is -1, we already know its integral. Its integral is natural log. Okay, so antiderivatives. We're going to talk more about this next time. I definitely want to do a little bit more of this. So just so you know what's going to happen on Friday. On Friday, we'll go over the quiz. I'm going to get that graded, and we'll talk about it since Friday's our last day of class. So we'll go over the quiz, go over any last-minute homework assignment questions. Then I want to talk a little bit more about antiderivatives. Because the more of them you see, the more you do, the better you're going to feel about it. And then we're going to spend the remaining time talking about the final exam. The final exam is going to be on Monday, right? Remember, it's on Monday. We'll talk more about the details of that on Friday, but it is cumulative. It's like anything goes. But this class has been kind of cumulative. We're still doing things that we did way back at the beginning, right? But we'll nail that down a little bit more on Friday. All right. So that's our plan. We're wrapping up here. So before I sign off, any other questions before we go? No? All right. Well, then with that, have an excellent couple of days, and I will see you all on Friday.